Alright, day 87 of 100 Days of Mel. Pretty ironic morning today, not gonna lie. Woke up at 5:30 but just stayed in bed for a whole 2 hours. But I'm just happy that I haven't skipped out on a day so far, and I'm pretty close to finishing. About 13 days left, which is around a little less than 2 weeks. Most likely gonna continue some sort of series after this, just to keep that habit of doing something every day. But I'll decide that later. So I'll be. Oh, why is this not working? It's supposed to be formatting it. It's not formatting it correctly. Let me check if I did this right. Yeah, so it has to be like this, followed by quotations and I mean, not quotations, but these brackets. I don't understand why it didn't format over here. I mean, this is a public link. So it's a public link as well. I don't know. I have to check it in GitHub. I mean, the local repository and see if something's going wrong here. Maybe changing it through GitHub is not really working. Okay, anyways, so what I'm going to be doing is reading EfficientNet. This is basically one of the papers that I got from the Berkeley reading list for machine learning. And in their introduction beginning guide, they have a list of papers that they suggest for starting out. And one of them is EfficientNet. And so today I'll be reading this paper. I want to try to utilize the technique that was talked about in yesterday's reading, the ability to kind of quickly go through a research paper, determine what it's about, and then decide whether or not it's worth the full read. So I'm going to go ahead and download this and put it into my iPad. Okay, I have it opened up. Alright, so first things first, going to start with the abstract, try to get a consensus of what the main points are in this paper, then immediately skip to one of the important sections, try to read that, and then see if the paper is worth the read. So let's go ahead and read the abstract. They have the code as well. It's nice. Most people don't have the code. I don't know why it's under the TPU for TensorFlow. That's odd. I wonder if TensorFlow has implementation of EfficientNet in its main repository. It looks like it does. It's under. It's under TFKRS, so it's, and it has like 7 different versions or more. 1, 2, 3, 4, 5, 6, 7, 8. Okay, anyways, going back to the paper. So it looks like from what the abstract is saying is that they basically try to scale up the normal convnets. And in this process, they're trying to carefully balance the network depth, width, and resolution for a better performance. And so this scaling method can scale all of these dimensions and effectively get a better result. So they come up with an effective coefficient, compound coefficient, to be the scaling factor. And using that, they design a new baseline network and scale it, and they called it EfficientNet. And while being 8.4 times smaller and 6 times faster, it does better on ImageNet and also CIFAR 100. Well, it doesn't really do the best. It's not really, you know, if you look at it here, it's not really compared to other models the best. Actually, it looks like it's doing fairly well, but I'm not sure if they handpicked these models. EfficientNet B7 seems to do pretty well in the top 1% accuracy. So yeah, we have ResNet over here, Inception. Seems to do pretty well. And yeah, and it also does transfer learning pretty well too. So that's a plus. And they have code on TensorFlow. I wonder who's this written by. Ming Sing Tang. Are these the people at Google? Yeah, staff research scientists at Google. Yes, Stanford. Also part of Google Brain. Goddamn. All right, so now let's try to identify where exactly the main work begins. Okay. So here is the scaling factorization, and they derive the factorization here in this section number 3, and then in section 4 they introduced the EfficientNet architecture using the scaling compound. So I think 3 and 4 are the main sections here, and 5 just goes into experiments and the results from their experiments. 6 is discussion, conclusion, rest of the papers. Okay, so let's start with 3 and see where we can go. Figure 2a illustrate a representative ConvNet where the spatial dimension general chunk, but the so the spatial dimension is gradually shrinking, and you can see that by the width resolution h by x, and eventually it shrinks down to a very thin line. But the channel dimension is expanding over the layers. So here the width is really small, gets a little bigger, 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 and then very big. But it's really small in height. Okay, so the problem formation section just sets up the definitions, notations, and whatnot. So here it starts off by defining what a usual convnet layer is, and by defining y of I is equal to f of I x of I, where f of I is the operator and y of I is the output tensor, and x of I is the input tensor. So some sort of output is determined by passing in the input tensor into some sort of operator. We don't need to directly specify what the operator is. And this is for one layer. And if we want to expand that to multiple layers, we have that notation over here where f of I, L of I is basically denoting the layer f of I is expanded to L of I times in the stage I. Not really sure what this circle and dot symbol is. It's pretty cool, but I have no idea what it means. Let's see. And it also talks about the dimensions where h of I, wi is the spatial dimension, and visually determining it, you can think about it as the height in this architecture, where the resolution is h and hw, and then c of I is the channel dimension, and in this diagram, it's basically the width of the layer. So the wider it is, the higher the channel dimension, and the taller it is, the higher the spatial dimension. And let's see what's next. All right, so they define this scaling function as a uniformly constant scaling metric, which scales h of I and w of I without changing the essential operator f of I. And so, in order to keep this a constant and also to make sure that the model isn't too complicated, they make the scaling factor uniform and with a constant ratio. Okay. So they continue to describe this coefficient, which is WD and R. W for width, D for depth, and R for resolution, and they all scale different factors of the ConvNet equation formulation. So the R and R scales both the resolution dimensions by scaling the spatial dimensions, and W, the width, scales up the channel dimension, and D increases the number of layers in the model. And so usually the common scaling factor is by increasing the depth of the convolution net. It's become like, a common thing that a deeper model can capture more complex and richer features. However, it becomes very difficult due to the fact of the vanishing gradient problem which arises, which ResNet tries to solve using its residual networks. But this paper also says that, as if you keep going, it'll still have diminishing accuracy returns. Next up, with the factor which is used for commonly used for smaller models, it tends to be able to capture fine-grained features and easier to train. And resolution captures more fine-grained patterns in a network. So one of the observations that is important that they say is that scaling up the dimension of a network improves the accuracy. However, the accuracy gain diminishes for bigger models. So in order to solve this issue, what they do is they try to balance all the dimensions of the network and resolution during the scaling. So they're uniformly scaling it with the constant factor. That's basically what it means. And that's what they're introducing in this paper, which is compound scaling. And so what we saw before, the DWR gets mapped into these values, alpha to the power of sigma. I think that's theta. I have no idea what that is, but okay, whatever. Alpha, beta, gamma, all to the power of some constant. And we also determined that a rule that alpha times beta squared times gamma squared approximately equal to 2, and they all have to be positive integers. And I think this value right here, approximately equal to 2, something to do with doubling the flops in the network depth. So there we go. That's basically the meat of the paper. And now what they're going to do is apply this compounding scaling to a regular ConvNet and create a new architecture calling it EfficientNet. So I'm going to go ahead and read that. Yeah, so it's pretty much the same thing. They fixed the theta value to 1, and then they start doing grid search on the alpha, beta, gamma values, and eventually scale it up. And so they scale it up from using the base network, which is B0, and they scale it from 1 to 7. And they eventually see that, they constantly does better through scaling. So that's pretty much the meat of this paper, which is pretty cool. One thing that I do want to learn is what are flops? Some sort of metric, but I don't understand. Measure the number of operations of a frozen deep learning network. Unit of speed. Yeah, I've heard like teraflops, teraflops, and stuff like that before. Teraflops. So I guess it means like speed, the amount of floating point operations per second. Like this has 12 teraflops. No idea. 9 TF flops. Measure the computer speed. And so yeah, they target trying to optimize flops rather than latency. So that's how they're able to make the network efficient. Okay. I think that concludes EfficientNet. I think the introduction and whatnot just sets up some of the convolution of ConvNet efficiency and accuracy. Might be something to look into. And the introduction just gives a basis on what the vision industry is doing currently. Okay, so next up, YOLO. I'm gonna try to do that tomorrow. Mm. And now, like, reading a paper went from a work of 7 days to essentially 1 day, even though I spent a significant amount of time today, around 40 minutes, mostly because my final's on in another 3 more days, so I have some time to study for that. Let's see, day 88. So tomorrow we're going to do YOLO. I think I've read this paper before, but I don't know if I fully try to grasp the mathematical formulations in the stated in the paper, so I'll try to read that properly. I think I know what's going wrong here. I'm trying to use this notation inside of a HTML tag, which is not going to work. I'm going to have to use the href tag, the a tag. That's okay. I'll fix it later. Maybe sometime later when I have some time. So read YOLO tomorrow, and that's it for today. I'll continue streaming tomorrow.